Okay. So good morning, everyone, and welcome to the February edition of GeoLesson webinar series. And I would especially like to thank you all for joining on Saturday. Today, we are honored to host Dr. Rakesh Salunke for our session on geotechnical asset management with remote sensing and geophysical methods for resilient infrastructure. Dr. Rakesh Salunke is a remote sensing scientist at Shannon and Wilson and a civil and geotechnical engineering professional with over 14 years of experience in both industry and academia in the United States. He holds a PhD in civil engineering and specializes in integrating remote sensing and geophysical technologies with advanced data analytics, including AI and machine learning for geohazard monitoring and infrastructure asset management. His expertise includes LiDAR, UAV photogrammetry, INSAR, hyperspectral imaging, ERI, and MASW, which he has applied to monitor landslides, sinkholes, and other geohazard affecting critical transportation and dam infrastructure. Before joining Shannon and Wilson, Dr. Salunke served as a postdoctoral researcher at Jackson State University. During his time at JSU, he was not only a dedicated researcher, but also a mentor and guiding presence for many of us. He was admired for his mentorship, thoughtful guidance, and dedication to fostering a supportive research culture. For many of us, he was someone we would always approach for guidance, a true mentor in both academia and professional growth. So we are truly grateful that he has taken the time to join us today and share his expertise. Please join me in welcoming Dr. Rakesh Salunke for his presentation.
Awesome. Thank you so much, Audrika, for that wonderful introduction. So with that, I would like to jump into the topic for today. Just to make sure I'm clearly audible to everybody, correct?
Yes.
Good. Good. So my topic, like Audrika mentioned, is going to be about geotechnical asset management with remote sensing and geophysical methods for resilient infrastructure. And this, I think, is a good segue from the last webinar in this series where geotechnical asset management was significantly discussed. And where the current state of geotechnical asset management is and where it should go in terms of trying to develop a resilient infrastructure is what I'll be discussing today. And before we jump into it, I wanted to quickly acknowledge that studies presented in this webinar were actually part of my dissertation and postdoctoral research work, and they were supported by and funded by several state and federal entities, including US DOT, Federal Highway Administration, Mississippi DOT, Federal Railway Administration, and National Science Foundation. And a quick disclaimer that the statements and views presented in this paper or in this study or in this presentation are strictly those of authors and not any positions held by the affiliations or funding agencies. So today's presentation outline, I would like to go over these specific sections, background, start with the background, talk about the different multi-sensing technologies, including remote sensing and geophysical techniques, talk about how these can be implemented for GAM or geotechnical asset management and risk assessment framework, and discuss, if time permits, to discuss a few case studies where these technologies can be applied within the GAM umbrella for different applications. And finally, end with summary. So quick introduction to those who are not familiar, but I doubt most of us have been practicing geotechnical engineering or studying it. So what are geotechnical assets? They can be classified into these four major ones, although there are several others that I haven't shown in these slides, but these four assets classes, embankments, cut slopes, retaining walls, and subgrades are significantly important for transportation infrastructure. What is geotechnical asset management? Simply put, it's managing these geotechnical assets. And specifically, today's talk will be focused more towards transportation infrastructure, but many of the findings or many of the impacts of this study can be applied to many other geotechnical assets as well, not just transportation, but natural resources, environmental, and other sectors as well. So geotechnical assets are the four, especially focused on the transportation infrastructure, retaining walls, slopes, embankments, and subgrades that support transportation assets, such as roads and bridges, right? So why are we discussing geotechnical asset management? Because transportation asset management as a whole is federally mandated, and but the major issue with here is it mostly focuses on pavements and bridges. Much of the funding that's assigned to transportation asset management is spent on these structures. However, we need to pay attention to embankment, slope, retaining walls, and subgrades, which significantly support or which are the backbones of these transportation assets. But however, in the many states, the geotechnical asset management is still not mandated. And why this is important is because transportation infrastructure assets depend on the performance of geotech assets, and managing the geotech assets will lead to maximizing the life cycle cost and risk reduction of transportation infrastructure as a whole. I wanted to quickly touch on the current GAM framework that has been proposed or established by or through a study that was done by NCHRP. NCHRP is the National Cooperative Highway Research Program. It's an entity under National Academies of Science. So many of the established protocols come through NCHRP studies. And this is the framework for geotechnical asset management currently that has been proposed or has been implemented. As you can see, the highlighted part here in the red dashed lines here, steps 1, 2, 3. These are the most important steps to make a GAM framework successful, because they involve identifying an asset, assigning a rating based on the present condition, and then determining the safety and mobility and different consequences if something were to happen to these assets. And then these three drive the actual steps that can be taken to further perform the assessment and then safeguard these assets. So the talk that I'm delivering today mainly discusses about these steps 2 and 3 mainly because, as you can see here, it says assign O&M rating based on the present condition. But if you're talking about a resilient infrastructure, you need to be thinking about projected risks or future states of assets and kind of plan for that. So that's part is kind of missing in this framework, which I will discuss heavily in today's talk, and how that can be incorporated using these advanced techniques. So problem statement, we already discussed why GAM is crucial for transportation infrastructure. And condition assessment and risk rating methods are currently based on qualitative factors. They are not really quantified, but just based on it's subjective based on the radar's inputs. And the assessments are kind of based on point monitoring methods as of now. For instance, what I mean here is this is a slope in the central Mississippi with boreholes on the left side of the slope here, but there's deformation on the right side where there's no data points collected from these borehole sensors. So that's what I mean by where the coverage is not asset-wide. So, and then there's lack of guide of integrating these information into an actual geotechnical asset management framework. Combine that with the different geohazards and different issues related to extreme weather, and also sensitive soil like expansive clay that is inherent to the geography in Mississippi, and extreme weather, including rate of change of precipitation, which is increasing over the past century. And then you see like it was discussed in the last webinar by Dr. Khan about how the infrastructure was not designed, or the embankments were not designed to act as a dam, where if there's a clog in the culverts and they're not able to withhold the pressure, it kind of results in a washout, or it results in slide failures and things of that nature. So with that background, a few more slides of different failures. I think a lot of these were already discussed, so I'm just gonna quickly say something about Hurricane Ida, where this struck the storm struck in 2021, in the fall of 2021. Although it entered like it made landfall in the coastal Mississippi and coastal Louisiana, it went all the way to northeast United States and still had enough power in it, and it didn't dissipate as usually the storms do when they make landfall. So the bottom two images that you see are damage caused by extreme rainfall from Hurricane Ida all the way in Pennsylvania and New Jersey. So that's the kind of effect we are dealing with here with the intensifying storms, and we need to be able to manage or manage these assets in a more like by incorporating resiliency into the mix. More pictures of washouts and slides and erosion-based failures impacting transportation assets. Again, more of the same. This is another 20 rainfall in 2022 in Mississippi, which resulted in erosion and scour impacting transportation assets, including railway and roadway bridges. Today's talk's focus will mostly be on embankments and slope assets because they significantly affect the highway and railway embankments and infrastructure assets. And several of the studies that I'll be presenting today will focus on the sites that that we studied as part of my research over the past 6 years in Jackson State University, and the slopes are located in the central, in the greater Jackson metro area or in and around central Mississippi. These are the study locations for different studies that were performed, and I'm going to jump into the different multi-sensing methods and how to incorporate these technologies or the data sets from these technologies for risk assessment for a resilient infrastructure. Starting with these three technologies here that are seen on this slide, UAV-based photogrammetry, including thermal and optical imagery, LiDAR, terrestrial or aerial. I don't have the picture of the aerial LiDAR here, but it is also included in our study, and geophysical methods like electrical resistivity imaging. Cross-platform data, use that for meaningful inferencing, and then develop methods for present condition assessment and future condition assessment, and then by kind of doing simulation-based studies, and then implement that integrate that into GAN framework. And what are the different technologies? I will just quickly go over the workflow, and we'll see the different methods that how they've been implemented. On the left-hand side, you see the DJI drone with the optical and thermal camera payloads. On the right side, you see the NDAA compliant quadcopter with hyperspectral and aerial LiDAR payloads. The workflow for UAV, most of you already know these, so I'm just going to quickly go over these. If you have any questions, we can discuss later. Licensed pilot gathers plans a mission and performs data acquisition, comes back and does data processing and georeferencing, which is a crucial step. Auto rectification, mosaicing, develop digital elevation model, and measurements of slopes, profiles, topography. Quick distinction I wanted to make here quickly is this workflow was followed for the Mississippi State Study 316, but there are several other ways you could use the data to as a structure from motion-based technology or photogrammetry to derive point clouds and not just digital elevation models, then use that to perform your surface deformation monitoring or change detection. So data processing, this is how it typically looks like. UAV flight path is used to tie together images and then orthomosaic them and then develop the 3D model. A typical image from a UAV thermal sensor. You see on the left side, there's a thermal image, and you can clearly see the different thermal signatures. The bridge is cooler. As assumed, the bridge deck is cooler than the approach embankment pavement, which is warmer because it sits on top of soil. But that's not just that, but even the side slope here next to the embankment, next to the crest here, you can see the different soil moisture accumulation spots can be identified. And the drier soil is warmer compared to the wet soil, and these can be used into your workflows to estimate soil moisture accumulation and things like that. LiDAR workflow is a little different for terrestrial versus UAV, but basically the underlying principle are same, where you get data and then register point clouds, georeference them, extract bare earth, and either do point cloud based change detection or use surface and then or create digital elevation models, and then do your measurements, slope profile changes, topography, and GIS integration. Typical setup of a terrestrial LiDAR is here's where we were collecting data on a map side slope at Sowell Road, Terry Road, and US 49 South, all in central Mississippi. Typical georeferencing, like if you have ground control points provided by the state, you just place your ground control mats there, and then collect coordinates based on GNSS. And if there's nothing, you make your own ground control points. That's the workflow. And this is a typical workflow which was implemented for this state study for Mississippi DOT. You use the point cloud, develop TIN-based surface models, and compare the multi-epoch surface models to develop slope variations over time. Electrical resistivity workflow includes setting up the electrical resistivity data or arrays with the electrodes sticking inside the ground, collect the data, perform resistivity inversion, develop 2D profiles, and then follow through the quality control, check the root mean square, and then do inferencing. We don't want to discuss the theory behind this today because of lack of time, but there are studies that we have published which can be studied to understand the theory behind this. But basically, we're trying to understand or measure the electrical resistivity of the subsurface by injecting electric current into the ground and measuring voltage across other electrodes. So this kind of tells us different things of the subsurface, like compaction of the soil layers, moisture accumulation, hydrological properties, if you want to explore groundwater, and different solute transfers in landfills or embankments. So this is a typical field data acquisition image. This is how data is collected. I wanted to quickly show some results of where these technologies were implemented on one of the failed slopes outside of Jackson, Mississippi. Here you see the UAV image. On the left side, you have the 3D digital model, and then the digital elevation model, which just shows the changes in elevation across the site. And based on the workflow that I discussed before, you can develop the slope profile at each time that the data was collected, and then you can superimpose the different DEMs or TIN surfaces to develop slope profile comparisons. So this was fall 2021. The previous slide, the current slide is fall 2022. So you have the data from multi-epochs, and then you superimpose them. Similarly, the same workflow for LiDAR also, but because it's point clouds, the accuracy is a little different. But basically, the principle is the same. You do the superimposition and then compare the slope profile variations over time. Resistivity, similarly, you do the same thing, that collect data at multiple timelines and then compare them. So here's a typical resistivity result. Like this is the cross-section profile of the subsurface at resistivity lines A and B. And you can see there's extent of failed area could be mapped based on the resistivity signatures, because loose soil has high resistivity versus wet soil has low resistivity. And wet and bound soil, like you can see the moisture logged areas under soil disturbances, which is showing the path of the water infiltration. And this kind of, based on the knowledge, specific knowledge of the sites and the type of soil and groundwater table, you can make inferences. And this can be used for geotechnical asset management, developing a geotechnical asset management framework, which I'll discuss shortly. So, Audrika, please tell me like if I'm going over time or anything like that, because I'm trying to monitor it, but just to be careful, I don't want to go over an hour. Okay, so. Right, thanks. So the GAM applications and risk assessment framework, where and how can these different technologies be applied for geotech asset management, right? So we discussed about the near surface remote sensing, LiDAR, drone, and then geophysical methods, ERI. Combining these with numerical modeling and back calculations, and then AI-based predictive modeling. Combine all these together, you can build an advanced geotechnical asset management framework, which you can implement on different assets. Currently, I'm going to talk only about embankments and slopes, but these can be used for subgrades, retaining walls, or other or like geotechnical assets like earth dams, levees, you name it. And how to use the outputs of these technologies or data sets collected using these advanced methods for risk quantification at present and future condition. Present condition is it tells us what the state of the asset is now. By doing simulation studies, you can project you can determine the projected state of the asset, which kind of helps us to plan for resiliency of the infrastructure. So one case study I want to present here, combining these three technologies with the workflow that we just discussed, combine the outputs of these to develop level of risk and condition assessment. So this was part of my dissertation study. So this is the risk assessment framework that we developed. Here we use the results from LiDAR and UAV and find out the surface deformation over time, and then use this electrical resistivity results to come up with the subsurface degree of saturation, because like I said, resistivity can be correlated with the moisture content or the degree of saturation based on existing correlations. And then combine these two with the finite element based stability analysis to come up with the factor of safety, which can tell you about the consequence, what happens based on the likelihood. So LHS stands for likelihood score, which tells you the current state. And then CS stands for consequence score, which assigns a score based on what would happen based on the state of the asset. So you combine these two into this simple equation, LHS1 times CS and LHS2. This should be LHS2, by the way, times CS, and then you get a level of risk. So the risk scale that we came up with was from 1 through 32. Where level of risk 1 means the asset is in great condition. Level of risk 32 means the risk to the asset is really high. So intervention is warranted. So the framework has this kind of chart here, like for surface deformation, anything under 2 inches, low score, anything under 6 inches or greater than 6 inches, high likelihood score. Now, this is subjective, or by subjective, what I mean is this is like, it can be flexible, like it depends on your different location. You can adjust these charts or metrics based on what location you're considering. But for this particular study, this was a good kind of these kind of metrics work well. And so surface deformation, you assign a likelihood score based on the comparison of different surface profiles over time. And then using the electrical resistivity correlation to degree of saturation, you come up with the relation is like it's inversely related. So Higher the degree of saturation, lower is the resistivity. So using that information for each section, wherever you want, you so wherever whatever section you want the state to identify the state of slope. So you just cut a line and figure out what the resistivity is, and then compare that with the correlation and come up with the degree of saturation. That will tell you kind of the perch water condition, which we know is a known problem in many of the assets or embankment and slope assets in central Mississippi. And based on that, you assign likelihood score. Again, same logic, lower score is lesser risk versus higher score is more risk. Finally, the consequence score, use the finite element-based modeling, come up with factor of safety for the slope. And this is again inversely related. Higher factor of safety means lower consequence score, which is good. So less consequence versus higher consequence score is bad. So with that framework, this is the kind of the final level of risk you get. You plug those numbers in the equation and you get these. So 32 is very high, 2 is low, which is good, and 32 is poor. So with that background, just quickly showing how we can apply this for assessing future risk. So in other words, accounting for resiliency in geotech asset management. So we just don't want to be concerned about the present state, but also the future state. So with that, this is a study that we did where Hurricane Ida was discussed in the last webinar. So we know this was a devastating storm that passed through the US in 2021. So using this as a case, what we did was, now we know there have been studies that have said that the storms are intensifying over time. So there might be a time in the future where the storm intensity, which is at the coastal area, can very well be like it can happen in the inland cities also, where the storms may not dissipate as quickly, the intensity may not dissipate as quickly as they used to, and they might drop high intensity rainfall in a short duration in the inland cities where the infrastructure is not prepared to handle that kind of load. So this was the kind of logic for this study where we simulated the same amount of rainfall that fell in Pascagoula, Mississippi, in the coastal Mississippi region, and the same level of intensity was simulated in Jackson, Mississippi, using Plaxis 2D flow modeling. And this is the typical workflow, creating geometry, creating a groundwater flow boundary for a particular slope, which we knew was in a good state because it was a repaired slope and was intact, and it had a high factor of safety. So we simulated this kind of rainfall on that slope using a discharge function. And what the finding was, as the precipitation increased for over a 7-day period, which was the span of the Hurricane Ida's impact around Mississippi and in the southeast. So the factor of safety fell to as low as 1.1, which is the critical. Getting to 1 is failure, right? So, but 1.1 is still kind of almost close to failure. So that is the slope is in a state of at the brink of failure. So if the conditions sustained further, or if there was another event that happened, the slope would definitely fail without giving the time for the water dissipation or the water runoff and things like that. So that's the consideration here. So what at the present state, the slope is intact. At the future state, it might very well fail. That's what the findings were. So, for instance, over here, the level of risk of at these two sections of the slope were very high to high, which means the transportation asset management aligned rating would say this is poor or at least in failure state. So the framework would look like this. So you get your surface information from LiDAR or UAV. And the beauty about this method is you don't need to assign a single rating for one slope of, let's say, 100-foot section. You can develop as many sections as you want, because a slope might look good on one side, but it might have a failure somewhere else. So it depends. It's kind of subjective. Like I said, if an inspector is looking at a slope where it's not failed, it might, I mean, it doesn't make sense. It's just failed at one point, right? So we would this method. What we can do is you can cut a line and find out what the score or the surface deformation is at that particular section, and at the same section you can find out if there's any perched water state or the moisture accumulation, and based on that you assign score, come up, and you integrate that with your numerical modeling and stability analysis for that particular slope, and come up with this with the level of risk score. So at the present condition, you see the level of risk 4 versus future condition after simulating heavy rainfall, it would be 32, which can be used to do like predictive or proactive maintenance, which was discussed, I believe, in the last webinar. So this is kind of how you can incorporate resiliency into your geotechnical asset management and plan like proactive maintenance rather than reactive maintenance. So the framework would look like this. You identify the asset, perform UAV and LiDAR scanning, find out whether active deformation. If there's nothing, just keep monitoring. If there is deformation, you deploy electrical resistivity imaging, because this is kind of a little labor intensive. So once you do that, if there is subsurface anomalies like perk water or waterlogged or something that is unusual, you continue the data integration and evaluation with further manual reviews and validations, then assign risk rankings. And then if it's a high risk geotech asset, by high risk, it means if it's going to lead to loss of life or property or something like that, you have to take immediate intervention. If not, you continue monitoring. So that's the framework. Now, since we might have another 5 or 10 minutes, correct? So I would like to quickly touch on different case studies that can be done using these remote sensing methods and geophysical methods. Case study 1, this was published recently in the Springer Scientific Reports, Springer Nature. So landslide susceptibility modeling of highway embankments using these methods, the remote sensing methods plus AI and ML predictive modeling. So using the data, the satellite-based data, LiDAR data, and drone satellite imagery, you develop causative factors like rasters of these different geomorphological and hydrological factors, and prepare training and test data, and train the different models to predict or classify the landslide susceptibility, and then identify the slope failure. But although these kind of studies have been done significantly or significantly applied towards identifying landslides in hilly regions, this study was specifically focusing on highway slopes. So the data was obtained from Mississippi Automated Research Information System and collected over past 2005 to 2017, and the resolution was about 0.7 meters. So this is the DEM from the LiDAR data, and the highways were segmented from that DEM, creating a buffer, and then different causative factor rasters were developed. And definitely random forest performed the best compared to the others, although it looks a little like an overfit model, but it's tweaking the data multiple times and doing significant statistical based studies like validations didn't change the results much, which means the random forest did perform the best. And this was the kind of the susceptibility map that we came up with. So this kind of matched with the existing, this is the corridor, I-55 corridor in central Mississippi, and the red spots show high susceptibility to failure, and the different influential or causative factors are listed here. And, the precipitation, NDVI, distance from streams, and elevation were the top 4 causative factors that influence the failures, according to this study. So that's one study. Another study is satellite-based INSAR. So this is another topic of mine that's I'm closely working on and I'm very interested in is applying satellite-based imagery, including INSAR, for ground deformation monitoring. And this involves using the phase differences from radar signals obtained every 6 to 12 days on a particular region of interest. So this is open source data, and you can use this to convert the radar phase shifts to deformation maps. And for an area, you can measure up to millimeter level changes over time. But in this case study, we combined the INSAR with our LiDAR and UAV workflows for validation, and presented this study in GeoFrontiers last year. And the study was focused on a couple of slopes again in central Mississippi. This slide over here shows the deformation map. It was converted using this tells us how much the ground moved between the years 2018 and 2024. The ground displacement patterns over the 6-year period, and the pixel over here is it's about 10-meter resolution. What we did was we identified where our slopes were in that raster and clipped the area and found what the displacements were over time. When we compared that with the LiDAR and UAV, the results were kind of close, which kind of validated our study. But however, it needs to be made clear that there are limitations by combining the INSAR-based or satellite-based study with the high-resolution LiDAR or UAV, because the limitations include less control over error mitigation, and comparison between low resolution and high resolution makes it challenging. But having said that, over the 6-year period, the changes from INSAR observed was about less than an inch. INSAR, while it indicated uplift, the LiDAR indicated settlement in that area, but since it's less plus or minus 1 inch, that is within the error margin. But for slope 2, the comparison was pretty close over the period of 6 years. So the reason I wanted to discuss this quickly was because this technology can be seamlessly integrated into this framework that I discussed earlier, where you just use INSAR to identify assets in areas with high ground motion. So instead of identifying the assets and then implementing this other framework, you use INSAR satellite-based study or the landslide susceptibility mapping to identify hotspot areas, and then go and implement your fine resolution data sets or data acquisition using UAV and LiDAR and electrical resistivity or MASW or other geophysical methods to come up with a risk rating and finding out the condition assessment of the assets. And finally, this is the last case study. Not going to spend much time on this. This is using UAV and thermal imagery and optical imagery, and using the intensity of the bands itself, you come up with the soil moisture estimation. This can be replaced with hyperspectral imagery, where soil and vegetation can be classified using the intensity signals of these bands. So this is just the results. It's showing the thermal-based soil moisture estimation. So finally, coming to the summary, I wanted to just quickly touch on how rapid and accurate investigation of geotechnical assets can be achieved using these advanced sensing methods. This can help with proactive asset protection for long-term safety. And then it advances the maturity of the GAM programs. Evidence from using the LiDAR, UAV, and ERI for assessment helps with it has shown that initial rapid screening for asset stress, including slope movements, settlements, and soil deformations, can be valuable. And then following that up with subsurface ERI or other geophysical methods like MASW and other things can tell us more about the subsurface information, which can be integrated into the larger GAM framework. And then you develop the condition assessment framework. So these, again, I'm not gonna, it's pretty much self-explanatory, but just wanted to touch that this is quite flexible with, can be seamlessly integrated with other technologies and also the assets can be substituted between embankment slopes, subgrades, or retaining walls and other geotechnical assets. So the benefits being you get risk assessment framework, not just at the present state, but also at the future projected state, which is very important for incorporating resiliency in our infrastructure maintenance. So with that, this is the final slide, I promise, just different technologies and the different applications. So LiDAR, UAV, AIML, soil moisture prediction, surface deformation, resistivity, use subsurface perched water high and high saturation zone identification, soil moisture suction estimation, which is important for soil slope stability and studies, back analysis using the ERI and UAV to kind of determine the geotechnical properties of the slope or the asset at the failure state. You could do that. There's a study that we did on that. And again, combining these three technologies to simulate extreme weather and future risk, which is important to incorporate resiliency in your asset management framework, and using LiDAR and GIS and AIML methods for failure susceptibility and satellite-based INSAR for surface deformation and failure susceptibility. So these are the different applications within the umbrella of the geotech asset management using these advanced multi-sensing tools. And with that, I wanted to end my talk today. Thank you very much for your attention. We can discuss any questions if you guys have anything to discuss.
Dr. Tariq has a raised hand. I have a question. Dr. Tariq, you're muted.
Now, can you hear me?
Yes.
Thank you, Dr. Rakesh, for excellent presentations. I could get a big picture of what is happening in our lab. So hyperspectral image is very effective, I find here in case of geotechnical asset management, also vegetations. How much it is effective in case of only the water body?
All right, so let me understand your question. So you're saying how
Yes.
important is hyperspectral imaging in understanding water bodies?
Only the water body. If say it is the oceans, only the water body, away from the embankments.
Yeah.
So if you work with only the water body, how much may be effective?
I mean, there satellite imagery or hyperspectral imagery, water has one particular signature. So you can identify water based on the hyperspectral band signal, correct? But if you want to monitor structure like soil and vegetation in marshlands, yes, there's a definite application for hyperspectral imaging. But usually when we do those kind of studies, we classify water and then we don't use that in the further classification of the different marshland vegetation or soil and things like that. So yeah, there are applications for hyperspectral. I mean, actually, it's significant applications for marshland monitoring.
Thank you very much.
Any more questions from the participants?
People are just waking up.
Dr. Salunke, I had a question, a bit different from the presentations. You mentioned working with the drones, and we know that UAV regulations are frequently updating. So during your time at JSU as well, you were always the proactive one, letting the team know what updates have been there on the drones and the regulatory changes, which were quite significant. So I mean, how do you stay updated on those evolving regulations? I mean, is there any specific source you recommend, or how often did you check on those websites?
So the best source is your funding agency. They usually get letters, like for instance, I believe recently all DOT funded or federally funded agencies were notified that you are not supposed to use any, not just Chinese, but some internationally manufactured drones. So you can rely on your funding agencies, or definitely go to FAA, bookmark FAA on your browser, and they'll definitely keep releasing like you watch their newsletters. Yeah, subscribe to them. That's it. That's the simplest way. Actually, go to the source. Why you wait for hear from the funding agencies? But having said that, I want to say that if your funding agency is okay with you using internationally purchased, like internationally manufactured drones, then you should be fine.
Thank you, Dr. Rakesh.
Hi, Dr. Rakesh. I want to ask one question to you.
Yes.
Thank you for the presentation, first of all. Now you are working in the industry, so how now you are seeing closely from the industry perspective. So how much they're reliable or dependent on like this kind of LiDAR or drone monitoring, or this kind of the GAM network that you showed today. Like how much they're evolving and how they are relying on that for monitoring.
Yeah. I cannot tell you like how much, like give you a percentage based answer. Like, okay, so much percentage of funds are set aside every year for this kind of monitoring. But I can tell you that, especially where I am right now, in the Pacific Northwest, here you have a lot of hilly mountainous regions, and the highways are built or cut slopes, like highways are built along cut slopes and tunnels and things like that. So remote sensing based monitoring is included in their asset management program for a while now, for over more than like 20 years, I think. But having said that, it's not actively done in every state, I believe. But it also, like I said again, so there are like state maintained highways, right? State DOT, where they have been actively trying to incorporate remote sensing technologies, including fixed cameras, UAV-based cameras for monitoring rock falls and things like that. And LiDAR change detection is also, I'm seeing that is growing in popularity. However, they still want a geotechnical engineer to verify that data. They just don't want to see by themselves and make decisions, but they still want an engineer to review that. If that makes sense.
Thank you.
Yeah,
go ahead.
Yeah, I just wanted to say that it's basically implemented for monitoring. Okay, it's not like it's not used for your design decisions or designing a structure. Like you designing, you still follow the same techniques that have been like at least for geotechnical design, but these technologies are heavily used for monitoring.
Got it. Thank you.
We maybe have time for one more question from the participants. Okay, so if there are no more questions, I would like to basically thank all of our participants for joining us this Saturday and your active engagement throughout the session. And obviously, thank you very much, Dr. Rakesh, for such a thoughtful and insightful, impactful presentation and for sharing your expertise with the GeoListen community. It's been basically a great learning experience for me as well. You kind of jotted everything, including the case by case description of the geotechnical asset management and everything. It was really helpful for me as well. So thank you very much for giving us the time and the opportunity to observe this presentation. So do you have any do you have any words for the
No, it was just
participants?
I enjoyed revisiting my research over the past 6 years that I did at Jackson State, brought back some good memories. So I just want to say that since many of the audience members here are with Jackson State, so I didn't do the study by my own. There were like hard work, sweat, and blood involved of many people within the career team to collect the data and process and build this kind of workflow and pipeline. So, and definitely Dr. Khan, his leadership helped in putting together a lot of these, research outputs. So, yeah, I had fun talking about it. See, Fahim yeah, sorry, go ahead.
No. You continue.
I said Fahim had a smile on his face. So I thought he wanted to say something.
Oh, is it like it's good to see you again?
Yeah, you as well.
Yeah, that's what I was about to say. It's good having you again.
Okay.
Here.
Next
Yeah,
time
you
not
can
virtually.
end the recording. We can chat some more.
Okay, so finally, just one closing remarks for those seeking the professional development hours. So participants who attended the live session will receive their PDH automatically. For those who were unable to attend the session, the recording will be uploaded to the GeoListen YouTube channel, and the link will be shared to the participants who registered for the webinar, and a short assessment link will be shared via email. So a minimum score of 80% will be required for the PDH credit. And we look forward to seeing you all in our upcoming GeoLesson session as well, which would be held in the last week of March, the details of which will be shared in our LinkedIn and website pages. So thank you once again and have a wonderful weekend, everybody.
Thank you.
Thank you.
Thank you, Rakesh.